Okay, recording is in progress. I think we can get started. So today our topic is combinatorial implications of max flow mean cut theorem. So first of all, I will guide you through to review the concepts and the theorems in max flow mean cut. So today's topic is combinatorial implication. Max flow mean cut. Okay, so first I want to ask you some question. So you know what is max flow, right? So I give you a network and I specify a source and a sink. So if you want to find a max flow, then that's to say you want to maximize the flow that goes out of the source, or equivalently, to maximize the flow that goes into the sink, right? And this is max flow, but what is mean cut? Sean, do you know? Do you still remember the definition of mean cut?
Is there like on two nodes and the flow goes into the nodes and the minimum of the flow goes into the nodes and out of the nodes. That's the opposite way.
Almost correct. Okay, so let me state it formally. So that's to say we want to partition our node set n. So when I say this word partition, so if I say partition a set, it means that I want to split this set into several different subsets. And these subsets should satisfy, first, they are disjoint with each other. And second, their union is just the whole set. So we want to partition a node set into S and T. So be careful, this is capital S. So and capital T, where our source S is in the capital S, and the sink T is in the capital T. Then the mean cut is equivalent to say what is the minimum of U, V, E. So what does this mean? This means that, say, this is the capital S, and this is the capital T. And then you need to make sure that your source node is in the capital S, and your sink node is in the capital T. Then this question says that UV in out S means that for all the arcs that goes from S to T, you want to maximize the capacity of these arcs. That's to say you need to divide them into S and T. So this is like an integer programming. Why do I say integer programming? It is equivalent to say, so you denote capital S as 0 and the capital T as 1. Then for every node, it can be 0 or 1. This is a combinatorial problem. So I think in the class, you have already learned a fact. The fact is that finding max flow, this is equivalent to finding mean cut. My question is why? Has Dr. Costello covered this fact in her lecture? Max flow is equivalent to finding mean cut. Okay, so I'll quickly go through it. So the reason why is that I given any flow, say F, on our graph G, and any ST cut on G. Then what you can say is that the value of your flow, this is equal to what? I give you any flow F on the graph G and any ST cut on G. Then the value of the flow, this is equal to the flow out of capital S minus the flow that goes into capital S. This is very, very straightforward, right? So definitely this is less than or equal to the flow that goes out of S. This inequality is very straightforward. And the flow that goes out of S is also less than or equal to sigma of UV in out S. That's to say, we sum over all the arc that goes from S to T, from capital S to capital T, and CUV. That's to say that the flow out of S is less than or equal to the capacity of the arcs that goes from S to T. And this is CST. This is the value of this cut, of this ST cut. So that's to say the flow is less than or equal to the capacity of a cut. So that's to say any flow is less than or equal to the value of any ST cut. So what can we say is that max flow is less than or equal to mean cut. Then, do you still remember how can we show that this is actually equal? Or in other words, how can you find this mean cut? How can you find this mean cut? Let me erase this. Okay, so today we're talking about combinatorial implication, maximum mean cut. So now we have shown that the max flow is less than or equal to the mean cut. Then our next step is to find the mean cut. Our next step is to find the mean cut. So the way is like this. So let's say we are given max flow F. Be careful that now we are assuming that we have already been given the max flow F. Then we construct the residual network. So if you forget some concepts of residual network, then you should review your notes. So for example, you are given a max flow F. And then you construct the residual network GF. So to find the minimum ST cut, what you need to do is to do BFS. Or you can also do DFS, whatever. Say / DFS from your source S. So what does this mean? So suppose you have already constructed the residual network GF, and then you do BFS from your source node S. What does a BFS return? It returns all the nodes that are accessible to S, right? In the residual network. So suppose this circle is a closure of the nodes that are accessible to S in the residual network. And this circle is a closure of the nodes that are not accessible to S. Okay, so then we can say, I claim that this is capital S, this is capital T. Or in other words, that's to say, the mean cut, the mean ST cut is like, it is in this way, such that S, okay, so S is all the nodes V, such that V is accessible to S in the residual network. Why? My question is why? Thomas, do you remember?
Well, why V is accessible?
Yeah, like you are given a max flow F. You construct the residual network GF, and you do BFS or DFS from your source. And these are the nodes that are accessible to S. These are the nodes that are not accessible to S. Then I claim that this is the mean cut. This is the mean cut. Why?
That's because all your max flow has to like cross the board arcs of the cut. So so that's why you I guess so we would know that at some point there would be a point in which I don't know. Something about region T.
Oh, okay, that's fine. Actually, it takes several steps to show this result. So first, we can say that if in GF, say it's too small. Let's say this is capital S. This is capital T. Okay. First, my question is this arc possible? Is this arc possible? Let's say we have some U here, we have some V here. Is this arc feasible? No, right? Because capital S is all the arcs that are accessible to your source node. Then if this arc UV exists, then V should also be in capital S. So this arc is impossible. This is my first claim. And so then what can we say about what can we say about arc UV such that U is in S, V is in T in original graph G. Be careful of this question. Now my question is, in the original graph G, not in the residual graph. So in the original graph G, what can we say about all the arc UV such that U is in S, V is in T? They should all be filled, right? Otherwise, there should be an arc UV. But if they are filled, then we only have arc VU in the residual network because they are filled. So that's to say, for all the U in S, V in T in the original graph G, we can say that the flow on UV is just equal to the capacity of UV. Then in the residual network, we only have VU, we don't have UV. Okay, so this is the first claim. That's to say all the arcs from S to T are filled. All arcs from S to T are filled. Okay. These are all the arcs from S to T are filled. Then, how about all arcs VU such that V is in T, U is in S in the original graph G. What can we say about them? All the arcs VU, so V is in T, U is in S, and VU exists in the original graph. What can we say about them? What criteria should the flow on VU satisfy? Think about it. So consider this case. What can we say about it? So we can say that the flow on VU is 0. Why? Because if there exists a flow on the VU, as you say, now suppose we have some V here and U here. If there exists some flow on VU, then in the residual network, there exists an arc from S to T, which is impossible, right? I've already claimed this here. So FVU must be 0. This is the second claim. All arcs from T to S are empty. So keep in mind these two claims. These are very important when you are solving problems about minimum cut. All the arcs, so in the minimum cut, all the arcs from S to T are filled, and all the arcs from T to S are empty. Remember how to prove this. I've already shown this here. Okay, so this is a review of the max flow min cut. Then let's talk about 3 theorems in your textbook. So what I'm talking about today is the section 6.6 in the textbook. So the first theorem, let me write it down. So max number of arc disjoint from S to T equals the number of arcs whose removal disconnects S. So what does this theorem say? The maximum number of arc disjoint paths from S to T. So this is like, so we have S, we have T. Arc disjoint path means that, so we have these paths, these paths, these paths, and they don't have any arc in common. This is called arc disjoint paths from S to T. This is equal to the minimum number of arcs whose removal disconnects S and T. So that's to say, what is the minimum number of arcs such that if you remove them, then S is disconnected from T. So this is the first theorem. I can provide 2 proofs. So the first proof is what I thought by myself. So let's just use some notation. So we let maximum number of arc disjoint paths from S to T, we let this to be K. And the minimum number of arcs whose removal disconnects S and T, we just name it to be M. So that's to say we want to show that K equals to M. Then first we can show that K is greater than or equal to M. Why do I say so? That's to say if I remove one arc on each of these arc disjoint paths, then S and T are disconnected, right? So that's to say K is an upper bound for M. Remember my reasoning. That's to say I just take away one arc on each of the paths. S and T are disconnected. So K is greater than or equal to M. K is an upper bound of M. And then we can show that K greater than M is wrong. Why? What is the reasoning? So the reasoning is for this is suppose we have K greater than M. Then if we remove M arcs, what happens? We have K arc disjoint paths from S to T. Then if we remove M arcs on this graph G, then we can at most disconnect M paths from S to T, right? This is called pigeonhole principle. We disconnect at most M paths from S to T. However, we have K greater than M. So that's to say S and T is still connected. So S, T still connected. Right. So that's to say in this proof, we first show that K is greater than or equal to M. And then I show that if K is strictly greater than M, this is impossible. So that's to say, so K equals to M. We are done. So I think if you want to prove something in this course, let's say you want to show something is equal to another, then common techniques may include you show that say you want to show A is equal to B, then you show that A is greater than or equal to B, and A is less than or equal to B. Then you can conclude that A is equal to B. Or you can show it in this way. You first show that A is greater than or equal to B, then you show that A greater than B is impossible. Then you can conclude that A is equal to B. These are just techniques. Okay, so this is my reasoning, but on the textbook, I saw a very clever proof. So what is the very clever proof? So we just we designed this problem into a max flow min cut problem. So let's we let each arc in the graph G have capacity 1. We let each arc in the graph G has capacity 1. Then we claim that max flow is just equal to K. Think about it why. Actually, I can tell you that for many problems, even if in the problem statement, you are not told that this is a max flow problem. You are not given the capacity of the arc. However, you can always transform it into a max flow min cut problem. So now if I let each arc in G have capacity 1, then because we have K arc disjoint paths from S to T, and every arc should have capacity 1, then the max flow is just equal to K. So think about it why. I think this is very straightforward. Then we find min cut. So if you want to find a min cut, make sure that you have already got the max flow. And you get a max flow, you construct the residual network, and you do the BFS from your source node S, then you can find the min cut, the min ST cut. And I claim that the min cut value is equal to M. This is also very straightforward, right? The min cut value is just equal to M. Oh, by the way, so has Dr. Costello told you how can we use the minimum cut theorem? Or in other words, what is the application of min cut? Has he told you? Okay, I can just give you one example. So suppose in a war, okay, so you combat with the enemy, and the enemy has a network G, and for on the network there are roads, and for every road there is a number. Number means that how much cost does it take to cut this road? Then what is the minimum cost for you to cut the supply chain of your enemy? for example, this is your enemy's warehouse. This is your enemy's, say, factory. They manufacture some weapons, and this is their army. And then you need to cut this network such that it costs you the least. However, you can just disconnect the manufacturer and the army. So this is one application. So that's to say, if you find the min cut, then the min cut value is equal to n. This is derived from the theorem that we have just said. So in the min cut, for all the arcs that goes from capital S to capital T, they are filled. And for all the arcs that goes from capital T to capital S, they are empty. Okay, so this is I think this is a very clever proof. All right, so next, we can talk about a very similar theorem. So similar theorem is like max number of node disjoint paths from S to T. This is equal to the minimum number of nodes whose removal these nodes S and T. So let's look at what it talks about. The maximum number of node disjoint paths from S to T is equal to the minimum number of nodes whose removal just disconnects S and T. So the difference is that now we are talking about node disjoint paths, and we are removing nodes rather than arcs compared with the previous theorem. Then how can we prove this by max flow? I'll give you some hint. The hint is to do a network transformation that we have. Oh, you can.
Yeah, I think that where we make all the arcs in the network nodes and all the nodes in the network arcs.
Then okay, so you make all the nodes to be the arc and all the arc to be the nodes, right? Then suppose this is a node. This is originally, right?
Yeah.
Then how can you convert it into, say, there are 3 arcs, then it becomes 3 nodes. Right, you cannot do it, right? Okay, so I give you some hint to do a network transformation using one technique that I introduced last week. Split. Yes, you are correct. So what we need to do is to do node splitting. But when we are doing node split, this is a very common technique for the network flow problem, node splitting. But when we are doing node splitting, I think in 99% of the cases, you just need to split all the nodes that are apart from S and T. That's to say, you don't need to split S and T. You just need to split all the intermediate nodes. Node splitting for all the node I, which is not T or S. Then for node I, becomes, say, I prime and I double prime. So what does it look like? Say, suppose in the original graph, we have node J points to node I. Then after splitting, what we need to do is like, okay, this J prime to J double prime and to I prime, I double prime. This is the node splitting. And then we can let C I prime, I double prime to be 1. So that's to say, I prime to I double prime, this has capacity 1. And J prime to J double prime, this also has capacity 1. But for the original arcs in the network, let's say in the original graph, you have Ji, you have the arc Ji. Then say suppose this has capacity Cji. Then from J double prime to I prime, you have Cj double prime, I prime. This is just equal to Cji. However, because now you have already split the nodes, then when I say I remove a node from the network, it is equivalent to say I cut. Say if I want to remove the node I, then it is equivalent to say after splitting, I cut I prime to I double prime, right? Then oh, excuse me, I made a mistake here. In the original network, you are not told the capacity of the arc, because originally when you get this problem, you are not told that okay, solve it by max flow problem. You are not told the capacity of the arc. So that's to say you are only given a network. Then a common technique for this is just let it to be infinity. Yeah, so, sorry about that. You are not told the capacity, the node capacity, the arc capacity. Okay, then we can claim that the left-hand side of this is left-hand side. The left-hand side of this is just equal to the max flow. And the right-hand side of this equation is just equal to the mean cut. Think about it why. Let's say the maximum number of node disjoint paths from S to T. This is just equal to the max flow. And the minimum number of nodes whose removal disconnects S and T. This is just the mean cut. So think about it why. And also here I can also tell you one thing. So in the transform network, suppose you have already found the max flow, right? And you also then you can also get the mean cut. What can we say about the mean cut? Say you have S, you have T, right? My question is it possible that say we have J double prime here and I prime here? Is this possible? Is this arc possible? No, it is not possible. Why? Because we have said that in the minimum cut, all the arcs that goes from S to T is filled. However, we know that J double prime to I prime, this has capacity infinity. Then if you want this arc to be filled, then the max flow is not bounded from above, which is impossible, right? Actually, even in this transform network, because you have arc capacity equals to 1 in each splitted node, then of course the max flow is bounded from above. So this is impossible. Keep in mind of this. And in the next theorem, when we are talking about bipartite graph, this will also be used. Whenever you have an arc that has capacity infinity, you should, when you see this, then you should know that in the mean cut, there should not such arc that goes from S to T, which has capacity infinity. Otherwise, the flow is not bounded from above. So this is the reasoning. The left-hand side is just equal to the max flow, and the right-hand side is equal to the mean cut. Think about it why. Okay, so next we talk about our last theorem today. So the last theorem is, let me write it down first. Okay, so this is our last theorem. So in a bipartite graph G, the max matching equals to the minimum node cover. So here are several concepts that I want to introduce. So first, what is a bipartite graph? In case that you have not studied graph theory before, so a bipartite graph is some graph such that you can partition your nodes into N1 and N2. And be careful of the definition that I told you. When I say a partition, it means that you have a set, you divide it into several subsets, and the subsets are disjoint with each other, and their union is just the entire set. This is a partition. So let's just say you partition the node set into N1 and N2. And then you can say that the arcs only exist between N1 and N2, but within N1, no arc. Within N2, no arc. This is called a bipartite graph. This is the first definition, bipartite graph. And what is a max matching? For any graph G, a matching means that you want to select a subset. Okay, so let me write it down. I think I need to write it down. So matching means that you need to select A prime, which is a subset of all the arcs. And because we know that it's a matching, as the name suggests, matching means that for all the arcs that are selected in this A prime, they should not have any node in common. So this is like pairing men and women together in a marriage problem. So matching, as the name suggests, the selected arcs should not have common nodes. This is matching. And what is a node cover? Node cover, it means that, say you have some graph G, then you want to select a subset of the nodes such that every arc has at least one node in this selected set. Right? No, this is called node cover. So node cover. That's to say you want to select N prime, which is a subset of N. And then every arc has at least one endpoint in this N prime. This is a node cover. And basically I can say that for max matching of any graph, not necessarily bipartite graph, the max matching, you can find it by some algorithm called Edmond-Blossom algorithm. And for minimum node cover, for any general graph, actually this is an NP-hard problem. Okay, so, but now we are talking about bipartite graphs. So here's a very, very useful technique, very useful technique. So suppose you are given this bipartite graph. Then what you need to do is to define a source S and a sink T. And then you connect S to every node in N1. And you connect every node in N2 to T. This is a very common technique. And then how to define the capacity. So we can just let the capacity of the arcs going from S to N1. They all have capacity 1. And here, for every arc that goes from N2 to T, they have capacity 1. And for all the arcs that in the middle, they have capacity infinity. So when you see infinity, you may have some impression that we have just talked about. Infinity, then when you are finding a mean cut, you don't have any arc that goes from S to T with infinity capacity, because the flow is bounded from above. So when you see infinity, you should think of something about the mean cut. Okay. So now I've constructed this network. I have artificially added S and artificially added T. Then we find the max flow. I want to claim that the max flow is just equal to max matching. Think about this, because for S that goes to every node in N1, they have capacity 1. And for all the nodes that goes from N2 to T, it also has capacity 1. Then suppose you find, suppose your flow goes in this way. Then for all the arcs between N1 and N2, if the flow on this arc is just equal to 1, then this is a matching, right? So by finding a max flow, you are finding a max matching. So max flow is equal to max matching. Then how can we claim that the mean cut is equal to the mean node cover? We need some reasoning here. I need to use a different color to suggest. Okay, so now suppose this is your S and this is your T. Okay, so we can just suppose, because now we are finding a mean cut, right? So suppose if we find the mean cut, S, the A and B, A is a subset of nodes in N1. B is a subset of nodes in N2. S, A, B are in the capital S. And so we have C here and D here, and also T. We suppose C, D, and T. These are in the capital T. Okay. So that's just a, so now let's consider the arcs. From S to A, is it possible? It's possible, right? Because the black is the capital T. From A to B, possible. And from C to D, possible. From D to T, possible. And from B to T is also possible, because here, B to T is also, not just possible, but definitely we have arcs from B to T. And from S to C, this is also possible. This is also definitely, because C is a subset of N1. Then, be very careful. The arcs from C to B, this is possible. However, the arcs from A to D is impossible. Why? Because for all the arcs in the middle, they have infinity capacity. Then because this is the mean cut, that's to say there should be no arc going from A to D. Otherwise the flow is not bounded from above. Because all the arcs going from A to D are filled, then the flow is not bounded from above, which is impossible. So there's no arc going from A to D, but just arc going from C to B. This is possible. This is just like you have some arc going from the capital T to capital S. This is possible. And we can also say that for all the arcs that goes from C to B, they are empty, no flow on it. Then we have figured out that we only have arcs in this manner. Then what is the minimum node cover? The minimum node cover is just you take out B and C, these two subsets of nodes. This is a node cover. Because in the original graph, you don't have S and T. Then, if you select out all the nodes in B and C, then for all the arcs in the original graph, it has at least one endpoint in B or C. Then you are done. The mean cut is just equal to the minimum node cover. Okay, so I have covered all the contents for today. So we still have 5 minutes left. So if you have any question, please ask. Otherwise, class is over. Thank you. Oh, by the way, this is very important. I remember I learned this in combinatorial optimization. So I didn't have any trouble in this course when dealing with problems about bipartite graph. So keep in mind that if you are given a bipartite graph, you should think of to artificially add a source node S and a sink node T. And you find a max flow in this manner. And this max flow can always help you to achieve some results. This is a very common technique.